Thank you. Right. Our highlight lecture is delivered by Kelvin Long, who's a member of the British Interplanetary Society. He can say maybe a little bit more about himself as he introduces himself, but we thought we'd like to end on looking at the prospects that one day, maybe, we'll travel further than the Moon, further than Mars, further even maybe than the solar system. So this is really Star Trek territory, I guess. And can I introduce, therefore, Kelvin, who will take us through this last lecture. Thank you.
Well, it's certainly a challenge to carry on from the astronauts. How do you progress these slides, sorry? Ah, there you go. Okay, so I'm certainly not an astronaut. I'm a member of the British Interplanetary Society, as was mentioned, so you might say I'm a bit of a space cadet, like a lot of people here. So I'm going to talk at the end of this, this wonderful conference about interstellar travel. So as if you need reminding about the achievements of spaceflight, here's some lovely pictures to start off with. So this is, of course, the International Space Station. Here's an astronaut driving a vehicle on the surface of the Moon. Here's a wonderful picture of Mars with its polar ice caps. And, of course, we've sent vehicles to Mars and taken pictures of the surface, and there's a vehicle there as we speak. We've sent spacecraft out to Saturn. We've looked close at the rings and realized about the structure of those and how complex they are. And, of course, Jupiter, which Galileo first looked at, is looking at its moons, and the prospects that there may even be a liquid ocean on the surface, within the sphere of Europa, which is very exciting. So in 2004, NASA decided to redirect its efforts, and it released the Vision for Space Exploration, is its new directive, which basically is all about developing Orion spacecraft by 2008 and conducting the first human spaceflight missions by 2014. They want to go on to the Moon by 2008, perhaps human missions by 2020, and eventually on to Mars. Very exciting and a very inspiring document. So, of course, what we really want to do one day is build spacecraft. Here's a spacecraft in orbit around Jupiter, perhaps mining some of the helium free from its atmosphere on towards the stars. And we want to see what other worlds look like out there in the universe other than the ones that we are used to. And of course, we want to know, is there life out there? So this is a beautiful picture of the Andromeda Galaxy M31, and we wonder if there is life forms, intelligent life forms there, looking back at us, wondering if there is intelligent life here. Of course, there isn't. And this is one of the pioneers of interstellar travel, Robert Ford. And he said, travel to the stars will be difficult and expensive. It will take decades of time, gigawatts of power, kilograms of mass energy, and trillions of dollars. Interstellar travel will always be difficult and expensive, but it can no longer be considered impossible. And that's the message of this presentation. In the past, people have thought about interstellar travel as being impossible. And hopefully, I'm going to show you a little bit that there are real schemes out there that have been designed. And interstellar travel is certainly not impossible. And these are the people that understood the issues. Here's another great pioneer, Arthur C. Clarke, of course, who passed away only recently. Many conservative scientists, appalled by these cosmic gulfs, have denied that they can ever be crossed. And again, they will be wrong, for they have failed to grasp the lesson of our age, that if something is possible in theory and no fundamental scientific laws oppose its realization, then sooner or later it will be achieved. Of course, Clarke was an optimist, but I certainly agree with his sentiments. So why not interstellar travel? Well, people say the stars are too far away, the travel times are far too long, you require enormous amounts of fuel, and of course, if you're sending astronauts, they have to spend a long time in zero gravity and a vacuum of space, and you may require closed cycle life support systems to support those astronauts. There's the obvious radiation hazards, and of course, impact of meteorite dust particles, which could impact the surface of your vehicle, and environmental impacts. People object to certain propulsion schemes involving detonation of explosions in the atmosphere are not particularly popular. And of course, why launch? Because 10 years later, you may have a better propulsion system which you launch and overtakes the one you sent before. So why not just wait till we've got something that's very fast? And of course, if you're going to go relativistic speeds, you have encounter the relativistic time dilation effect, so you could be separated from your loved ones you leave back home. So let's go to the more interesting topic, why interstellar travel? Of course, the sun has a finite age, 5 billion years, so it's not going to be here forever, and so we need to think about us, the Earth. When it gets eventually overpopulated, where are we going to go? Do we have sufficient energy sources to sustain us as a civilization? And of course, we would like to find habitable worlds and potentially life that may be out there. We'd like to build upon the achievements of spaceflight, which is clearly still happening today. The Apollo missions were over, and people worried about would we forget how to do that in the future. Clearly, we're returning to that. When we want to become an outward-looking society, particularly if we are to encounter any life forms out there in the rest of the universe. And the scientific advancements from pushing the boundaries of spaceflight, of course, are obvious. And if we can meet ET, that would be a wonderful thing, as long as he doesn't intend to destroy us. And of course, there's the cosmic perspective, understanding the overall purpose of humanity in the universe. What is our purpose of being here, if there is a purpose, and how do we fit into that structure? So here's just an illustration of some of the distances involved in interstellar travel. So an astronomical unit is roughly the distance from the Sun to the Earth, 10 to the power of 11 meters. And 1 light year is about 63,000 astronomical units. So those are enormous distances. But let's just think about what we've achieved to date. So the International Space Station, the shuttle, the satellites are all around 0.003 astronomical units. A very small number. Let's look when you go to interplanetary travel, out to, say, as far as Pluto. You're talking about 40 astronomical units. If you go further to the edge of the actual Kuiper Belt and the Oort cloud, you're talking much larger distances, 500 astronomical units and 50,000 astronomical units. And you can see the numbers going up and up and up. And eventually, I have to start using scientific notation because the numbers become so big. So interstellar travel, the nearest star, Alpha Centauri, 270,000 astronomical units away. And of course, the nearest galaxy, M31, 100 billion astronomical units away. Vast distances, and the challenge is really great, unlike anything we've ever encountered before. So if you could launch a spacecraft, where would you go? Of course, the Sun is on the Hertzsprung-Russell diagram of stellar structure. For those of you aware of it, is a G2-type yellow dwarf. So maybe you want to go somewhere where there are stars which are similar. And so close to us, within 20 light years, there are maybe less than 10 yellow-type dwarf G systems. And so most of the local neighborhood stars are what we call M-class. And indeed, within a 70 light-year radius from the Earth, there is about 100 or so G-type stars. So maybe you want to go there first and start to look at possibilities of being worlds. So some of the candidates, of course, is Alpha Centauri. People always talk about that, 4.3 light-years away. Maybe Epsilon Eridani, 11.2 light-years away, or even Tau Ceti, and there's many others. And so here's a picture just showing a comparison of the size difference with the Alpha Centauri Proxima system compared to the Sun. And of course, what we really want to do is find planets outside of our solar system, and this is the exoplanet program, which we are discovering many at the moment, and everyone was excited when they discovered Glasgow 581c, because maybe around 5 times the mass of the Earth. Very exciting. Perhaps D is an even more better candidate. So let's think about the linear velocities you have to actually obtain in order to go to the nearest stars. So let's just forget the fact that Alpha Centauri is out of the ecliptic plane, and let's just think about what sort of speed you need if you were to go to 4.3 light-years away. So as you can see, if you're traveling at 1 kilometers per second, you need to be pushing at those speeds. It's going to take you over 1 million years to get to the nearest star. So really, what you want to be pushing is around 10,000 kilometers per second, of order 3% of the speed of light, in order to get there in under a century or so. So that's the sort of speed you're looking at in order to get to the nearest stars. Vaster speeds compared to what we're doing today. So of course, today we have the Pioneer 10 and 11 spacecraft, the Voyager 1 and the Voyager 2 spacecraft, which are all pushing sort of 17-ish kilometers per second, 2 to 4 astronomical units per year. Quite a snail's pace, all launched in the 1970s. And we have the New Horizons mission launched in 2006, similar sort of speed. At those speeds, if they were to carry on to the nearest line of sight star, it would take of order 30 to 40,000 years. So clearly the propulsion technology is not there yet. And so ideally what we'd like to do is to go straight to the speed of light, and go straight to Alpha Centauri, send a radio signal back, and maybe after 9 years, we've got some information about that system. Of course, we can't really do that. What we really have to do is we have to accelerate, and then we have to cruise, and then perhaps to decelerate if you want to do some in situ science. And so let's think about some of the ways you could do that. So maybe you want to accelerate to 0.01 g to about 0.01 c times the speed of light. And maybe your data return, once you've sent your signal, will be over 400 years. And so you think, well, okay, so let's accelerate for slightly longer, achieve a slightly higher velocity, and reduce it to a century or so. And so you can start to play around with these sorts of mission profiles to think about, well, what do I need to do in order to get there within, say, 15 years? And the ideal would be to go at, of course, accelerate straight to relativistic speeds and get there within a decade or so. But what this produces, this is the Daedalus profile, roughly, which accelerated for 0.03 of acceleration up to about 0.0 c of the speed of light. And then there was a further 2-year cruise acceleration period of 0.06 g up to about 12% of the speed of light. This is Daedalus, which I'll talk a bit more about later, which was designed to go to the Barnard star. And so what this produces, when you start to look at these numbers, is acceleration, mission duration, and velocity requirements. You don't want to go too slow because it would just take too long. You don't want to go too fast because you hit the relativistic limit anyway. So maybe you want to accelerate at about 0.1 g. And you want to get there in under maybe half a century because that's the lifetime of the scientists involved, so there's continuity there, they can see the project through to fruition. And perhaps you want to be pushing about 0.3 times the speed of light, which is the sort of number you need to get there in a decent time. And so how can you do this? Well, there's several ways. You've got, of course, propellant housed within a vehicle, which powers it forward. So chemical, plasma type systems. You could, of course, take the fuel away from the vehicle and send it to the vehicle and deliver it as it's moving along, such as a laser system. Or you can be really clever, and if you could design a warp drive or a wormhole, and you could fly through an interstellar shortcut through space. And so there's two sort of ways of thinking about this. One is to have a very short mission, maybe 50 years, which would be ideal. So very high velocity, high specific impulse perhaps, mission. But it's considered that requires quite a large technology jump. The other way to do it is maybe a century, 1,000 years, much more modest time profile, using low velocity, high specific impulse engines. And that will require a much more modest technology jump than the one before. And so what can you do to get around that? Well, let's just think about what sort of energy is involved to propel a vehicle along to, say, up to a third of the speed of light. If you just take the kinetic energy, which, of course, is all about the velocity, the different types of propulsion systems you could use, and you can work out what the energy you need to impart to that system to give it the kinetic energy to move it forward. And you can do some simple numbers. So you take a simple 1-ton vehicle mass, and it would need about 10 to the power of 18 joules of energy, around 50 gigawatts, which is not too dissimilar to sort of nuclear reactor type levels. If you go to something a lot larger, like Battlestar Galactica type sizes, 100,000 tons, you need much greater amounts of energy, 10 to the power of 23 joules, and that's about 5 petawatts of energy. And so you can start to think about what those sort of power requirements are. But the bottom line is to push a 1-ton vehicle to about a third of the speed of light, you need about 50 gigawatts. Now, of course, basic rocket engines work on the principle of combusting a fuel and an oxidant at high temperature to give you your combustion products and propel the vehicle forward. And what determines all this is, of course, the thrust. Now, the thrust is there a laser pen here? Nope, no laser pen. The thrust is basically dependent upon the mass flow rate of the fuel. So you take something like the space shuttle, it's chucking reaction products out the back, and it's able to accelerate at quite high velocity for a very short time. And what the exhaust velocity really depends on is two main factors. One is the temperature of the combustion products, and of course you eventually hit a physical limit, because as you have higher and higher temperature, you can get more velocity, but eventually you may start to melt the vehicle as you hit the melting temperatures of the materials. So there's a real practical physical limit to what you can obtain. The other thing it depends on is inversely the molecular weight of the fuels you're using. So you might start to play around with using lower weight fuels. But eventually with chemical propellants you hit a limit. And so you have to start to turn to other systems. Now when you look at different rocket systems, what you have to think about is what's called the specific impulse, which is the velocity of your exhaust products divided by the gravity at sea level. Now, basically what it's telling you is how long your engine is going to burn for, and it's a measure of the efficiency of that engine, how much thrust you're getting, pounds of thrust per pounds of fuel you're using. And the other thing you turn to is this wonderful thing called the ideal rocket equation, which tells you what sort of burn velocity you need. And you can invert this to give you this relation here, which is the initial mass of your vehicle, thank you, divided by your mass of your vehicle after the fuel's all combusted. Right? And basically what this tells you is what sort of velocity you need to be going at with your different chemical systems or whatever systems you're using to retain your velocity you want. So if, for example, you're using chemical systems, maybe going 5 kilometers per second, and you wanted to go at 1/10 of 1% of the speed of light, which is about 300 kilometers per second, then you'd need about a mass of the fuel, about 10 to the power of 26 times the mass of your vehicle. And that's called the mass fraction, which is clearly unrealistic. So you have to start to turn to alternative propulsion systems. And so this is just showing the limits that you can obtain. And so we have the chemical systems, such as the Space Shuttle and the Saturn V, and they have these physical limits because they're using chemical fuels. So other ways you could do it, you could build what's called generation ships and just launch a whole team of willing astronauts who may be keen and may not necessarily be bothered about coming back. We heard earlier that perhaps they are. And it could take 1,000 years to get there, having lots of generations of children along the way. You could turn to alternative systems. People talk about nuclear energy, so fission reactors, for example. And there's been experiments, we're playing around with that with the rover and NOVA programs earlier on half a century just gone. And so there's electric systems which use electric and magnetic fields to heat and accelerate particles out the back. The problem with these systems is they have very low they have very low velocities, although the specific impulse is quite large. So you can gradually build up to a decent velocity. And so you can turn to alternative systems, such as the VASIMIR, Variable Specific Impulse Magnetoplasma Rocket, quite a long title, invented by Franklin Dyers in the United States, a former astronaut. And this is a really exciting technology, because it's a combination of the high-thrust, low-specific impulse systems like the Space Shuttle, and low-thrust, high-specific impulse systems like the electric propulsion techniques. And in theory, it's a prototype for how you might do fusion propulsion in the future. So it's quite an exciting technology, and its technological fruition is very close, although, as you can see, the speeds are still quite limited to around 300 kilometers per second. And how this works is to ionize a gas, so you strip off the electrons from the atoms, and you energize it using radio frequency heating technique, and then you accelerate those particles rearwards to give you your thrust generation. Now, there's been other projects historically. In 1976, the US NASA project called the 1,000 Astronomical Unit mission to get to 1,000 astronomical units. And this used a nuclear electric rocket, which would give you about 12,000 seconds specific impulse. That's how long the engine would essentially burn for. And it used about 40 tons of liquid xenon, and it would attain 100 kilometers per second with a 10-year burn, and reach 1,000 astronomical units within, say, 50 years. But at that speed, you're still talking about 12,000 years to get to Alpha Centauri. So people say, well, let's get away from the mass fraction problem and actually use something like the sun. The sun has a lot of heat energy, so the photons from the sun carry momentum, so perhaps we can build a huge sail, deliver those photons to this sail, which will be a reflective surface, low density, very thin, quite a large area, and that will propel the vehicle along. The problem, of course, is as you move away from the sun, the intensity of those photons will fall off with distance squared. So unfortunately, so does gravity, so once you achieve your cruise velocity, you should be able to carry on at those speeds. So people think, well, why don't we just build a big laser in space? So huge lens, Fresnel lens, get that energy, converge it, and then send a narrow collimated beam out into space and continue to propel that vehicle to higher and higher velocities. All these wonderful ideas that exist out there. Now, another idea is the nuclear pulse engine, which is the idea of ejecting nuclear bombs out the back of your vehicle and propelling your vehicle forward. Now, this, of course, was a serious scientific study in the 1950s by the US Air Force and others, because it went through various hands as it was managed. And it was a serious project. It cost about $11 million over 7 years. And the payload mass was about 20,000 tons, and the total mass was 400,000 tons for the sort of main reference vehicles. So these are very big systems. And they would use around 300,000 bombs weighing around a 1 ton each. And they'd be exploded maybe 1 every 3 seconds and push the vehicle at 1G. And so after 10 days, accelerating at that rate, maybe you'd attain 3% of the speed of light and get to Alpha Centauri in a century or so. Now, the key to this technology was to push a plate at the back. You explode these bombs, and the question was, would they ablate the surface? And the answer generally was thought, no, they wouldn't. And they have these wonderful shock absorbers, which would take that impact, and the crew, if they're there, would be right at the top, all safe and warm. And generally, people who worked in this project, such as Freeman Dyson, generally believed that they would be going to Saturn within their lifetimes. Of course, that didn't happen. One of the interesting things about this technology, though, whatever it's controversial, is it is the only high-specific impulse, high-thrust technology that could have been built yesterday. If we had an emergency such as an asteroid and we wanted to send something there within 10 years to impart some deflection mechanism, that will be the only technology we really have that's viable to do that. But, of course, it would be very controversial. And so we turn to other ideas, such as fusion, suggested over many times, but in 1966, for example, Spencer at NASA JPL suggested using deuterium and helium-free fusion to attain 60% of the speed of light velocities, and take about 50 years to get to Alpha Centauri. And Daedalus in 1970's British Interplanetary Society project, which I'll mention shortly, also would use deuterium and helium-free. And it was estimated that it would use around 30,000 tons of helium-free and 20,000 tons of deuterium. And, of course, they would collect it from the atmosphere of Jupiter, because we didn't know where else we could get this helium-free from, or perhaps even the solar wind. Now, the exciting thing is we've now discovered, we believe, about 1 million tons of helium-free on the moon, so people are excited about that. But the problem is how much energy you need to impart to extract that helium-free. It may actually be more, and therefore not worth trying to mine it. But the prospects of fusion-based propulsion systems are certainly improved as you move away from the external-driven pulse with these nuclear bombs to the internal-driven pulse with these fusion-type concepts. So inertial confinement fusion is something really interesting. Of course, the sun is a huge plasma, and its gravitational field is what confines it and allows those fusion reactions to occur at very high temperatures. A tokamak is a magnetic confinement system, which we're using in several reactors today to try and investigate that technology. Inertial confinement fusion uses the inertia of the material itself to confine that plasma. So you could take gases such as deuterium and tritium and react them to give you helium-4 and, say, a neutron. Problem is a neutron is radioactive and it's neutral, so you can't use magnetic fields to direct it outwards for the thrust. So maybe you want to use deuterium and helium-3, so it gives you your helium-4 particle and your proton. The proton it doesn't have radioactive properties, so you don't need to worry about that so much. The shielding constraints won't be as large. And because it has charge, you can use the magnetic fields to move it outwards. Now, of course, how inertial confinement fusion works is you have a gas surrounded by central pressure material, and you simply impart laser beams to it to cause it to implode, and this compresses the central gas up to very high temperatures and high velocities. And so what you get is eventually self-ignition in the center and the generation of what are called alpha particles, helium particles. And then they start to move outwards, and you get what's called a propagating thermonuclear burn wave outwards through this material. And eventually, the whole thing is ignited, and you've got your fusion energy. That's the principle of inertial confinement fusion. And I've mentioned these different types of reactions you can use. So Daedalus talked about the deuterium helium-3 reactions as the preference, but there are lots of others. It's a bit more difficult to get to that reaction because you require a slightly higher temperature. But there are lots of others you could use. And so in the fusion community, they have this thing called the Lawson's criteria, which basically relates the confinement time of your plasma to the number density of your particles and the temperature. And so you want it to be a certain number, which is about more than or equal to 10 to the power of 21 in these units. So for 10 kilo-electron-volt plasma, which is the temperature, you want the confinement time multiplied by the number density of the particles to be about 10 to the power of 20 in those units. And so a magnetic confinement, which is these tokamak systems, what they do is they use much less number density, smaller number density, 10 to the minus 6, and they confine that for quite a long time, a few seconds, to give you your fusion energy. Whereas inertial confinement fusion will use a much higher number density of particles and confine it for a much shorter period, like a nanosecond. Now, in the United States, they're building, of course, the National Ignition Facility, which is almost ready, and these are the numbers for the sort of properties you need to obtain at the central hotspot and the fuel outside in order to give you your fusion. So things are really moving forward in this field. Now, historically, in Culham in Oxford, we've had the JET, the Joint European Torus, which started operation in 1983. And at one point, they obtained about 40 megawatts of fusion power for a second. And of course, ITER, the International Thermonuclear Experimental Reactor, which is due to come online in 2018 in France, which could generate up to 500 megawatts of fusion power for 1,000 seconds. Very exciting. Now, in the inertial confinement fusion side, I mentioned NIF, which could generate up to 100 megajoules fusion power for a nanosecond or less. And there is even a proposal for something called HYPER, which could start construction in maybe 2010, which is an inertial confinement fusion prototype system, which could really push this technology forward. So people have always said fusion is always 20 or 30 years away, but there's a lot of exciting research going on. And the question is, could we use these results and this fusion research that's going on to power vehicles in the future? Could we engineer that technology? Now, I mentioned Daedalus earlier, so I guess it's about time for me to mention it a bit more. So this is a picture of Daedalus. And of course, Daedalus was a project of the British Interplanetary Society in the 1970s, and there are several members of that team in the audience today. And I mentioned the sort of cruise profile and acceleration profile it would use, but it was quite an amazing project for its time, and still is today. But basically, it would attain a velocity of about 10,000 kilometers per second and cruise for about 46 years and get to its target star, which was Barnard star, using deuterium and helium-3. Now, you can buy the report for the Project Daedalus from the British Interplanetary Society, and it remains today certainly one of the most complete interstellar studies ever conducted that I am aware of. Now, of course, there have been other projects in the 1980s, that shouldn't say 1897. There has been VISTA, Vehicle for Interplanetary Space Transport Applications in the United States, which also looked at using inertial confinement fusion to power a space vehicle and perhaps to get to Mars within 6 months. There's been other projects such as the US Navy Project Longshot, also use inertial confinement fusion, deuterium and helium-3 as the fuel, which could add a specific impulse of around 1 million seconds and achieve a decent fraction of the speed of light. So there's been these studies done historically. Now, of course, people are excited about antimatter because potentially you can get 100 times the energy from nuclear reactions for an antimatter reaction. The problem, of course, is we can't develop enough quantities of it. But if we could, that would be very exciting. And one of the exciting research ideas is to combine antimatter, i.e. send in a beam of antiprotons into an inertial confinement fusion capsule to help to ignite that fusion reaction and give you a lot more energy in the release. Now, of course, everyone's excited about wormholes because we love the science fiction programs on television, and it would be nice if we could just open up a wormhole like in Deep Space Nine, fly through it and come outside in another part of the universe. And, of course, people are also interested in schemes such as the warp drive, which uses perfectly constructive mathematical techniques and based on Einstein's theory of general relativity. And, of course, we all know that at the beginning of the universe it expanded very fast, and that was space itself expanding. And we know that stars collapse into black holes, for example, that's space collapsing. So space is kind of a movable fabric. We know we can manipulate space. And so the idea of the warp drive, of course, is to collapse space in front of a vehicle so that the distant objects come closer to you, and to expand space behind you, like at the beginning of the universe, so the close objects go farther away from you. The beauty of this scheme is the vehicle is trapped within a bubble with its own space-time, and the vehicle can go along without suffering any relativistic time dilation effects. So you can come home and your wife is still the same age as when you left. So really exciting technology. The problem of these things, same as the wormholes, is they require negative energy, enormous amounts. Current best estimates for warp drive, we're talking about a quarter of the mass of the sun for something of the size of 100 meters. So really at the moment it's very much conjecture, and we have to turn to alternative, more plausible schemes. And this is, of course, a subset of what we call the space drive. Could we engineer the quantum vacuum energy of space to give us your propulsive effect or some other property? Now, of course, you then have to be able to select between all these different schemes. This 10 to the power of 22 was an estimate from Bob Ford that he had once estimated the different combinations of propulsion schemes that he thought there may be. So there's an enormous amount of variety of different ways you can do space propulsion for interstellar missions. So how do you select between them? And, of course, you have to really look at the technology maturity. Let's just think about some of these schemes. So I've talked about the space shuttle, and it's very limited because it uses these chemical engines, maybe a specific impulse of 480 seconds, and it would take thousands and thousands of years to get to the Alpha Centauri. And the same with Saturn V, which used the same technology, and that shot fast really fast. And, of course, there's the electric propulsion schemes, which we are used to, which are being used quite frequently now in space. And they have very long specific impulses, as I mentioned, but their velocities aren't so great, although they do build up over time. But really, you're still talking about thousands of years for electric propulsion system to, say, get to Alpha Centauri. So what other options are there? Well, I mentioned NERVA, nuclear reactor rockets, having a nuclear reactor on an actual spacecraft. Maybe with that technology, you can get specific impulses of 3,000 seconds in theory and get there within 43,000 years. Still not good enough. What else can we use? Well, I've mentioned the 1,000 astronomical unit mission, which is a combination of nuclear and electric propulsion techniques. Still takes thousands of years to get to Alpha Centauri. And I mentioned this plasma drive system, very exciting technology, but still limited in the time it will take to get to the nearest star. And I mentioned the nuclear pulse, external nuclear pulse system, 130 years to the nearest star. Very a decent time scale. Perhaps you could design a mission that would take that long. But what we're really talking about is this lovely project, Daedalus, which I'm obviously flagging up today, which maybe would take 40 years or so, achieving specific impulses of 1 million seconds or more. Very exciting technology. And people say, well, why not, actually, rather than carrying the fusion fuel on board, why don't we just collect it as we go along? There's diffused hydrogen and helium throughout space. As we go along, we funnel it in, we ignite the fusion reactions, and perhaps, that could help us. But with that technology, the specific impulses are decent, but it'll still take quite a long years to get to the nearest star. And I mentioned solar cells earlier. Solar cell technology is really exciting and is certainly moving on, but we're talking about 43 years to get to the nearest star at those sorts of speeds. And people have suggested, rather than just sending a laser beam, why don't you send microwave energy, because it's much more efficient. And perhaps you could do that, but the technology has not really been demonstrated. And, of course, I mentioned the laser pulse. There certainly is a practical way to do it if you could put the technology together and get you there within a decent time period. And so we start to turn to antimatter. We love antimatter if we could find more of it. And of course, the warp drive is not really limited in its speed in theory. Maybe it can go several times the speed of light if you could put the technology together. And of course, wormholes. And of course, you start to look at these different propulsion schemes and start to categorize them. So what's high thrust, what's high specific impulse, and vice versa. And you start to group them into categories. And you start to see there's general trends. And of course, we've got the very fanciful systems such as the wormhole, the warp drive, maybe antimatter at the top can go very fast, but we don't have the technology maturity to develop those today. And the more practical but low specific impulse systems such as the shuttle and the Saturn V. So maybe you want something in between. So you really start to address the technology and you see what's accessible and what's speculative in the future. And that's how you have to really start to distinguish between them. And of course, the further into the future you try to predict, the uncertainty is even larger. So it's a difficult thing to do. So in the aerospace industry, we use something called technology readiness levels. So you start with something such as a wormhole, the warp drive type concepts, which we would call conjecture. And maybe something like the shuttle and the Saturn V, we've tested the application several times, and so that we would call that the TRL level of 9. And so the objective in the future will be to increase systems such as the fusion-based propulsion systems, perhaps these solar cell concepts, and maybe things like the plasma drive, which is moving on, increase their technological maturity so that we can push that technology forward and really demonstrate its application for different missions. Okay, so I'm going to start to quicken up a bit because I don't have much time. So in America, NASA had this thing called the National Institute for Advanced Concepts, which was a very exciting study, which spent a lot of money looking at a lot of different projects. Now, these are some of the projects they looked at, and it was cancelled a few years back. So they looked at solar cells for interstellar travel, plasma power, pulse generator, antimatter systems, anti-proton-driven systems, things which people might consider conjectural or speculative. And that project, unfortunately, finished. We also had the NASA Breakthrough Propulsion Physics Program, which came up with 3 really things you want to start to look at for interstellar travel. So you want to look at reducing the mass of a vehicle. Propulsion that requires no propellant would be ideal. Speed, propulsion that circumvents existing speed limit. Speed of light, is that possible or is that restricted? Energy, so new ways of producing energy production. And so some of the projects that they looked at were things like, can you vary the inertia of a body by varying the electric field, that sort of thing, and negative energy systems, and a whole raft of different studies. And that was an exciting project, which again, unfortunately, finished. And so where do we go from there? I'm going to skip that slide. So what we need is something to replace those sorts of organizations and the fantastic work they were doing, particularly in the private sector. So what we need is something that can take ideas or proposals from people, whether it's a university or a private individual or a space society, that says, hey, we've got this really great idea for a space propulsion system, and we want to use it to power a vehicle. We want to do a theoretical study. We want to do this small experiment to see if it's plausible or is it completely speculative. And so what you need is some sort of assessment where you could filter out the more feasible concepts from those which are very speculative, because it takes time and energy if you just look at the speculative ones, and then try and enable some sort of funding prospects for people to pursue these sorts of studies. And so the sort of things that organisation would look at is rigorous peer-review type research, looking at credible studies for space propulsion ideas in the future, and a whole raft of new ideas, whether it's new spacecraft or new experiments, to explore new properties that could help us. And so today, what we're really focused on is the International Space Station, low Earth orbit operations, returning to the Moon, future landings on Mars, and astronomy and planetary-based science. Really exciting stuff, and I'm really glad to see that all moving forward. So interstellar work is very theoretical in nature, and people still don't take it serious. And part of the problem, I believe, personal opinion, is the culture of the way we do science and how we allocate funding in particular. And the inclusiveness of science and non-academics. Today, it's not very inclusive. And so there's a whole raft of things we could do. And so we all heard about the X Prize earlier and how fantastic the achievement was there. Wouldn't it be nice if we could capture the spirit of the X Prize and try to push forward some of the technology, to think one day maybe we could push the technology to go to the Kuiper Belt, the Oort cloud, and perhaps eventually to the nearest stars. We need that spirit to be captured, and the private industry really needs to contribute towards that. And that's what the Tau Zero Foundation, which I'm representing today, aims to do. So the Tau Zero Foundation is a group of volunteer scientists, engineers, artists, writers, entrepreneurs from all over the world. And we're all dedicated towards interstellar travel and the dream of that and what vision that gives us. And it's a non-profit corporation, it's a registered charity, supported through donations. And basically what it aims to do is to fill the research gap in the market. So what the NASA Institute for Advanced Concepts was doing, what BPP was doing, this is what sort of thing we want to do. Although we also want to look at not just the speculative concepts, but the more realistic practical concepts, such as the Vasimir plasma drive type systems. So it's not just about breakthrough propulsion physics. We're not a space advocacy group, so we're not trying to lobby Parliament or Congress. We just want to do pure research and move the vision forward using credible science. And this is our motto, ad astra incrementis, which follows on for the British Interplanetary Society, which is ad astra. We accept that in principle, going to the stars could take many generations. That's possible. And so we want to move forward incrementally and to demonstrate the technology. And so in the future, it has been launched. The web page is available for you to look at, and you can see the link below. But in the future, the sort of things we'd like to do is to support students through scholarships, for example. Provide inspirational educational products, whether that's talks such as I'm giving today. Attend international conferences and perhaps even organise them, all dedicated towards the interstellar vision. And of course, what we'd like to do is to support interstellar studies, actual real designs for vehicles which could be launched within a century or more. And this would have to be, there'd be a filter process, so you select ideas and you get those which are more plausible, and you try to support those people to get their experimental results or fund them. So if somebody wanted to do a PhD, for example, in some fusion-based science which could help towards the propulsion, Tau Zero would fund them. That's the idea. And it seeks credible, rigorous scientific research. So we're making sure that we do things rigorously as we move forward. And eventually to give cash awards for visionary research, a bit like the X Prize. So you can join that if you look at the website and find out all about it. Now, just to finish off in the last couple of slides, so the message here has been really to hopefully talk to you a little bit about what people perceive as the impossibility of interstellar travel. There are many schemes out there today. There are hundreds of different ideas. You only have to look at the literature to see that. And it's certainly the literature shows that it's not impossible. It is possible to get to the stars within half a century or certainly a century if we can push the technology forward. It may not happen next week or the next decade, possibly even not this century, but it certainly will happen, and it's not impossible. What's going to bring all that together? Well, it's the vision. The vision, of course, is going to the stars and all of the wonderful knowledge returns we would get from that and what we will learn about science. The leadership which Tau Zero hopes to provide to lead the international community towards the research effort towards making this possible. And of course the courage to put together missions for spaceflight which are high risk but high gain, have a lot of high innovation. That's what we'd like to see. You have to accept that there are failures in space missions, and you have to put forward bold proposals to really get the real science gains. And of course the science, basing it on sound science, rigorous physics proposals, and bringing that together with the engineering to put together plausible concepts for precursor missions perhaps that could be launched in decades ahead. And so it's a question of why we want to do it, where we want to go, and how we want to do it, and when, and I've answered some of those. It's not a question of if, and I'm sure most people here do believe that one day we will go to the stars. And so I will leave on that last slide. Thank you.
Well, that's a really futuristic note to conclude on. I seem to remember something about an engineer called Scotty and the laws of physics, and you cannot do something with the laws of physics, Jim. A really futuristic note to end on. We have time for a couple of questions. If you'd like to stick your hand up, we do have the roving microphone. So who's going to volunteer to start taking us to the stars? Question. Yes, there we are.
Almost got away.
Rob Staley with the Jet Propulsion Laboratory. A great place to work for 30-some years. Maybe someday the first interstellar travel research will come out of a place like that. But there's a social question here, which you alluded to at the beginning. How do you think we ought to convince the world that this is the right thing to do?
I think that we have to demonstrate by gradual demonstration of the technology. For example, if we carry on the way we're going to be on Mars within decades. That seems to be clear to me. If we can do that, and people can see that we can do deep space missions, and then people could start to see that it's not just pie in the sky. It's very difficult to separate some of the technology from science fiction. And so what you have to do is to show that the results which come out of those studies is peer-reviewed, it's scientific, it's not just based on conjecture, and it's carefully caveated, so that certainly the scientific community can see that the proposals that are coming out are not claiming things such as the warp drive is possible within decades, and it's more likely thousands of years away if it ever was possible. I think that's the way to go forward, but it's by demonstrating the technology and increasing the technology readiness levels. But I think that the work that people have done, such as at Jet Propulsion Laboratory, is inspirational, and perhaps, as you say, future mission, some of the templates of that could come out of those sorts of institutes.
Hi there, my name is Shauna Pandya. I'm a medical student from the University of Alberta, so completely unrelated, but actually this sort of goes off your last question. I think the way to get society involved is show them that this is actually relevant to them. So have you talked about spin-offs or looked into the possibility of spin-offs of these technologies, and if so, what are they?
Yes. There is lots of discussions going on about carrying on some of the projects in the past, revisiting some of those projects. Those are international discussions. There are several countries involved in those, and lots of different ideas being revisited that were looked at in the 60s and the 70s and later. And so when you look at something like the Project Daedalus in the 1970s, and you look later, there were lots of papers that were published in the 1980s which were addressing some of the issues of the Daedalus project. And so there's enormous literature review that you have to go through to understand all the different issues. And so people are still picking up those problems and working on them. But what I would like to see is dedicated designs being looked at, not necessarily blueprints, but something which is at least giving you an idea of what the technology will look like. So taking some of the old projects perhaps, moving that forward, increasing what I call the technology readiness level of that technology. Perhaps you could do some experiments on the Earth to demonstrate that the technology works. And I alluded to fusion and exciting developments there. And I think that's how is the way to go for the future.
Roger Moses, University of Bristol. I enjoyed your talk, and I agree with you basically that things look more optimistic. The fact that JET has run for 10 seconds continuous means that we have practical fusion power, not tomorrow, but in the next decade or so. One of the issues that Daedalus raised outside the propulsion issue is that we don't actually know how to build machinery that will last for 100 years reliably and operate. We don't know how to build maintenance systems. We don't know how to build artificial intelligence to make the vehicle reliable over that very long operating lifetime. Have you given any thought to these other issues?
Yeah, my answer is get there quick. Daedalus, of course, looked at the idea of using onboard repair as you're going along. If you're going to send a vehicle that's going to take 50 years plus, you need to be able to make onboard repairs. Otherwise, it will be sad when you get that radio signal saying, sorry, got to 100 astronomical units and the system's fouled. Everyone will be very disappointed. So you have to have onboard repair systems. That is all linked to the artificial intelligence work that's going on. I was talking about that to somebody this afternoon. So there is work going on, and when I say, I'm perhaps giving the impression I'm just concentrating on the propulsion, but Tau Zero, British Interplanetary Society, lots of other organisations are all thinking about all the other areas, artificial intelligence, how that links to onboard repairs or sending a precursor probe. But, you know, we're pushing the technology forward. Voyager and Pioneer have been up there for years, still going, sending radio signals very weakly back. So as we do more, we'll learn how to do even more. We have to do the work to learn what's required.
We have time for possibly one more question, if there is one. Yes, down here.
Raise your hand. Who was it?
Sorry? Over here, yes.
Thanks very much. Nick Spall, also BIS. One way of, I suppose, cheating a bit on human star travel would be hibernation. Is anybody doing any research, or has there been any research on that aspect, more biological, obviously?
Oh, there is. You only have to look at the literature. People are looking at it. I'm not a specialist in that field, so I can't say too much about it, but I am aware there is work going on. Looking at animals that can hibernate, how that relates to humans. Could we do something to our immune system so that we could perhaps lower our body temperatures and our heart rate so we can survive a much longer time? Of course, in the 2001 story, Space Odyssey, that's what they did. They had hibernation and they were woke up when they got to Jupiter or Saturn in the actual book. So there is work going on. And I'm aware of that work, but I'm not a specialist in that field. So I sort of don't want to comment too much on it. But I'm sure it's very exciting research. I guess I'm more keen on getting there quickly within a few decades using high specific impulse, high thrust technology, high velocity, such as Daedalus type things, rather than sending everyone to sleep for 100 years and they wake up when they get there, if they do wake up. So, yeah.
Well,
okay.
thank you. I think we have to take that as the last question. I can see the crew for the closing ceremony is assembling at the back of the hall there. And the closing ceremony will take place in a few moments' time here in the auditorium. Could I ask you, therefore, to thank Kelvin for closing this conference in terms of presentations on a very futuristic note which takes us full circle back to what our imagination inspires us to do. Thank you, Kelvin.